This lesson is on simplifying radicals. As you can see, if you look at all the examples, radicals are basically like square roots. So if we look at the opener up at the top, assessing what you know, when we have square root of 81, that's 9. Square root of 64 is 8. Square root of 100 is 10. And if I have a square root of a fraction here, 25 over 4, I can separate square root of 25 over square root of 4. So square root of 25 is 5, square root of 4 is 2, and I get 5 halves. We can do all of these without a calculator because all 5 of the numbers that we had underneath square roots are what we call a perfect square. So let's list the first 15 perfect square numbers just so that we're easily able to recognize those moving forward. So what we're basically doing is taking the square root, or thinking backwards to find the perfect squares. Take like 1 squared, 2 squared, 3 squared, and so on. So we get a 1. 2 squared, or 2 times 2 is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. And 15 squared is 225. So if we ever have a square root with any of these numbers underneath, we can simplify to get, a whole number. And we don't have a decimal or anything else as long as it's a perfect square. So it's important that we recognize, like in our 4 problems above, that if there's any time that these numbers are under the root, then you can simplify that. All right, the next part is the multiplication property for square roots. And that looks like this, where the square root of a times b is equal to the square root of a times the square root of b. We're using this property in the next couple examples. And notice in example 1, we're starting with 2 separate roots, like the right side of this, and we're going to kind of multiply together and make it look like the left side, where we put them together under one root. But then in example 2, we're working backwards, and now we're starting with a number under the root, breaking it up to 2 separate numbers, and now we're going in this direction, starting with what's on the left and making it look like what's on the right. So we're going to use this property in both directions. Okay, here let me show you example 1. Starts like this, looks like this, and then example 2 starts like this, and it'll look like that. All right, so example 1. Square root of 2 times square root of 5. Well, we can do square root of 2 times 5 together under one root, and 2 times 5 is 10, so my answer is root 10. Is 10 on my list of perfect squares? No, so I just leave it, root 10. With part B, if you want to show that step in the middle, go ahead where you're doing the square root of 6 times 5, but I'm just going to go right to the answer. 6 times 5 is 30, so I get root 30. Notice you could say square root of 30. You could also say root 30 for short. You could also say radical 30. So there's many different ways of saying that answer out loud. Now in part C, when I multiply 3 and 12 together, under the radical I have 36. And since 36 is up here on our list of perfect square numbers, we know square root of 36 is equal to 6. So if it can be simplified, make sure you simplify that. And that's what our next section is about, simplifying radicals. So sometimes it can be simplified even if that number is not a perfect square. But if the number underneath the radical can divide by a perfect square number, you can also simplify. So in example 2, with root 18, 18 is not on our list above, but 9 is, and 9 is a factor of 18. So what the 3 little bullet points here with the check marks are saying is that a square root is in simplest form if no radicands can have perfect square factors other than 1. So up here, 10 has no factors on the list above besides 1. It doesn't divide by 4 or 9 or any of those other numbers higher than it. 30 also doesn't divide by 4 or 9 or 16 or 25 and so on. All right, the goal when simplifying radicals is to free as much as possible from under the root. We do this by looking for perfect square factors and simplifying. So let's look at some examples, and then this should make a little more sense. Now with root 18, I know 18 is 6 times 3. So is this equal to root 6 times root 3? Yes. However, can I take the square root of 6? No. Can I take the square root of 3? No. So breaking it down by these two numbers doesn't help out at all. That's why we have to know these perfect squares very well, because we want to find a factor of 18 that is on this list. So if you even go up and look at the numbers less than 18, you have 16, 9, and 4. Start with, you want to find the highest one possible. So if you start with 16, can 18 divide by 16? No. Can I divide by 9? Yes. So instead of using 6 and 3, we want to break this up with 9 and 2. So root 18 is equal to root 9 times root 2. The square root of 9 is a 3. Notice that the square root is now gone. Root 9 is equal to 3. Square root of 2 cannot be simplified, so I leave it exactly how it is, square root of 2. And this is my final answer. On these problems, I do encourage you to show this middle step of work. Don't try to go right to your final answer, or you might switch these and have the 2 on the outside and the 3 under the root and all that. So showing the work here is important. We're up here, since you were just multiplying two numbers together, it was fine to do that right away. Let's look at another one. Now 20 can be 1 times 20, 2 times 10, 4 times 5. But what number can it divide by on my list above? 4. So I can break it up, root 4, root 5, and root 4 becomes a 2, root 5. Okay, so when we look above, once again, our step was to find perfect square factors. In part A, 9 is a factor of 18, and it's a perfect square. And in part B, 4 is a factor of 20, and that's a perfect square. So we want to use those numbers, because then we can take the square root of that, and that simplifies our answer. 8 also divides by 4. So I could break up 8 with 4 times 2, which means root 8 is root 4, root 2. Once again, I'm just using the property above, where I am now starting with one number under the root, breaking it up like this. I'm just changing 8 to 4 times 2, then separating the two roots, root 4, root 2. So to finish this problem, root 4 is a 2, root 2 stays root 2, and my answer is 2 root 2. All right, there are 3 more problems with numbers that are not perfect squares, but they do all have a factor that is a perfect square from the list above. So please hit pause, try D, E, and F, and when you are ready to check your answers, then hit play again. All right, let's see how you did on these. So for part D, root 27, you can break up as root 9, root 3, and final answer is 3 root 3. Part E, let me show you what some people may have done here. Root 200, 200 can divide by 4, which is on my list above. And I can break it up as root 4, root 50, and root 4 becomes a 2. And then I have 2 root 50. Now 2 root 50 is equivalent to root 200. However, this is not simplified all the way. 50 can still divide by another number on that list, 25. So what I would have to do then is, I have my 2, I don't want to forget about that, break up 50 as 25 times 2, and then the square root of 25 can become a 5. So I have 2 times 5 times root 2, and then I can multiply 2 and 5 together to get 10 root 2. And we'll do more problems like this on the next page. My point here is, if you don't pick the biggest perfect square factor right away, that's okay. You can still keep going and get to the correct answer in the end. But there's a quicker way of doing this. If right away we recognize that 100 is a factor of 200, and 100 is a perfect square from our list above, then instead of using 4 and 50, I could do 100 and 2, root 100, root 2. Root 100 is 10, and then I have root 2. And look how much faster it was to get the same answer. So 200 can divide by 4. It can divide by 25. If it can divide by both 4 and 25, then 4 times 25 is 100. It can also divide by 100. So when you're trying to look at the list above, that's why with the, I think with the 18, I had said, let's look at all these numbers less than 18. Try to start with the highest one if you can. Okay, so when I'm trying to look at numbers that can divide by 200, start at the high end and work your way lower to find the highest one possible first. All right, letter F has root 28. 28 can divide by 4, so I can break it up root 4, root 7. And my final answer here is 2 root 7. So those are the 3 answers to the U-try. If we look at example 3, it is pretty similar to example 1. We have root 24, so I could break this down. Since 24 divides by 4 and nothing higher, it doesn't divide by 9 or 16 or 25 or anything bigger. So I can break it up root 4, root 6, and my final answer is 2 root 6. Make sure that the root with a number where it can't be simplified doesn't change at all. Don't make that root go away. Now the root with the perfect square, the root does go away because we change root 4 to 2. Okay, for some reason, a lot of times a common mistake students make is kind of switching those numbers. Okay, but the 6, the root stays with it. Okay, and then root 4 is just a 2, not a root 2. So try not to make those errors. Root 40, 40 can divide by 4 10 times. So I have root 4, root 10. Answer here is 2 root 10. Okay, now C, part C has root 15. Well, 15, it's not a prime number. It can have factors of 1 and 15 or 3 and 5, but none of these, well, besides 1, none of these other numbers are on our list above. So this is already simplified. So there's nothing to do to simplify root 15 because it doesn't have any perfect square factors. Root 29, same thing. 29 does not divide by 25 or 16 or 9 or 4. The only number on that list that it can divide by is a 1. And also 29 is even prime. So if the only factors are 1 in itself, then since 29 is not a perfect square, there's nothing to do there either. So that is also simplified. So root 29 just stays root 29. All right, we have 2 more examples. So if we look at example 4, we have a root 5 times a root 10. So what I'm going to do is put the numbers together under one square root, like we did in example 1. Root 5 times 10, and 5 times 10 is 50, so I have root 50. Now that I've put those together, now I'm going to break it up, but I'm not going to break it up using the 5 and the 10. I'm going to break it up using any factors that are perfect squares so I can simplify them. So 50, we already saw earlier, can divide by 25, which is on the list. So if I break it down by root 25, root 2, then root 25 is a 5, and root 2 stays root 2. Okay. For part B, we have root 3 times root 15. So if I put 3 and 15 together under one root, that multiplies to 45. So I kind of skipped this step this time of just putting 3 and 15 together under one root. I just multiplied the 2 right away. Now 45 can divide by 9, so I can break it down root 9, root 5, and root 9 becomes a 3, root 5. Now I'm going to show you one more option because on the problems, depending on the numbers, like here, I think I like this way of doing it in purple, but let me just show you in blue something else that will get you the same answer. So I'm going back to part A, I had a root 5, and now what you also could do with the root 10 is break it up to root 5, root 2. As long as you know how to multiply root 5 times root 5. excuse me, I actually think on the front page, I skipped that part. So let's come back and look at that. All right, so if you ever have root a times root a, meaning you have the same number under both roots, if I put it together, that'd be root a times a, and that is the same as root a squared. Now, if it's a squared, it has to be a perfect square because that's what a perfect square is, a number squared. And what happens is the square root and the square just cancel each other out, and I just get a. So root a times root a is equal to a. Let me just give you a couple more examples. That's saying that root 2 times root 2 is equal to 2, which makes sense because that would be root 4, which is 2. Root 3 times root 3 is equal to root 9, which is 3. You could also think of it as root 3 squared, and the squared and square root cancel each other out. So root 4 times root 4, you could think of this as root 16, which is a 4, or root 4 squared. Square and square root cancel out, you get a 4. Root 5 times root 5 is 5. Root 6 times root 6 is 6. So, going back up here, when I have root 5 times root 5, that just becomes a 5, and then I have a root 2. So just another way of doing these problems. Same thing here, if I break up the 15, root 3, root 5, then I have root 3 times root 3 is 3, and then a root 5, and I get the same answer. Okay? All right, so moving on to part C, no matter which method you use here, it shouldn't matter in the end, but I'm going to go ahead and combine. 2 times 6 is 12. Root 12 can break down to root 4, root 3, and then my final answer is 2, root 3. And the last one, we just talked about this. Root 5 times root 5 is 5. No need to show any work there. Done. Now, just to explain that once more, you could do root 5 times 5, which is 25, and that's how we also get 5. Or we could have thought of this as root 5 times 5. Instead of multiplying that to 25, like I did on the left side here, I could rewrite 5 times 5 as 5 squared, and now the square and the square root cancel, and I just get a 5. All right, last section for today. We actually kind of already saw this up above on example 1E when I had that 2 out in front of the root 50. So we're going to have the same thing here where there's a number out in front. So you just need to make sure you don't forget about that number. So I'm going to rewrite the 5, but now the root 12 is the part I'm going to try to simplify. So since 12 can divide by 4 3 times, we can break it down by root 4, root 3. Once again, I want to use these numbers because 4 is on my list of perfect squares. For example, root 6 and root 2 is also equal to root 12, but I can't simplify root 2 or root 6. Now the only thing I can change here is this root 4. So I'm going to have a 5 and a root 3 that don't change at all. The root 4 becomes a 2. Just be careful, this isn't 52. It's 5 times 2 times root 3. So now I can multiply 5 times 2 to get 10, root 3, and there's my final answer. Why is this more simplified than what we started with? Because the number under the radical is a 3, which you can't square root that, or it doesn't divide by any perfect squares. Where up above, the 12 is under a root, and it does divide by 4 from our list. All right. Here we're multiplying 2 root 3 and 4 root 12. So basically these numbers outside the roots we can multiply together. So 2 times 4 is 8. And then the numbers underneath the roots we can multiply together. So 3 times 12 is 36. Now since root 36 is a 6, the root goes away. 8 times 6 is 48, and there's our final answer. So we're kind of separately multiplying these numbers outside the roots together, and then we separately multiply these numbers underneath the root together. Why don't you go ahead and try part C, hit pause. When you get an answer, then go ahead and hit play to check it. So in part C, the 3 will just stay by itself outside, but under the root, I can multiply 2 and 10 together to get 20. And then I can break down root 20 to root 4, root 5. Root 4 becomes a 2. So the 3 doesn't change, the root 5 doesn't change, but now I can multiply 3 and 2 together to get 6 root 5. And there's the final answer. And I believe that is it. So that concludes our lesson on simplifying radicals. Just remember that for a radical to be simplified, today our focus was just making sure that it has no perfect square factors. So in other words, the number under the square root cannot divide by 4, 9, 16, 25, and so on from our list. So make sure you know those first 15 perfect squares.